I have the pleasure to introduce our next speaker. He has quite an interesting history. He's originally Bulgarian and won a number of international Olympiad awards. You can ask him about that during the breaks. He was he got the gold medal in math and informatics back in the in 1989. And by the way, because we have an amazing number of Eastern European computer scientists lately, it's just an incredible, I think it has a lot to do with these Olympiads. So I think we need to start these Olympiads back in the US. Anyway, they're very successful. He came to the US, he has a degree from MIT in cognitive science. He studied with Mike Jordan, I believe, at that time, and they have, I think, his most cited paper is with Mike. He spent some time at University College London. Then he spent time at USC, then UC San Diego, and then most recently has moved to the University of Washington, and where he heads a major lab there. Emo has written extensively on optimality. Optimal control and biomechanics. He is the originator of the iterative LQG algorithm. He's worked on analyzing human motor cortex signals and applied a number of new results in learning, which I hopefully will be talking about today, in robot and mechanical system learning. He's also the founder of the famous physics engine MuJoCo. So please join me in welcoming Emo.
So I'm going to be talking about model-based optimization and how to combine it with all the excitement that's going on in deep learning, but I'm from more of a control background, and so this would sound more traditional, like a class that, say, Claire Tomlin might teach. So I think we can all agree that some kind of optimization is the key to getting intelligent systems to work, and so the question is how to do it, and there are lots of ways to do optimization. Focusing in control, what I'm plotting here is a Pareto front. Like, level of automation is here, and data efficiency is here. And RL and neural networks and deep learning, what I'm going to call non-parametric optimization, meaning they have lots of parameters. They're highly automated, but they need plenty of data for now. Model-based optimization, without talk about, is somewhere in the middle. And we also have human optimization. So if you look at what Boston Dynamics does, they also do optimization. You know, they set up some control architecture, and then they go tweak the gains, except they're incredibly good at it. So it takes them ridiculously small amounts of data, like maybe on the order of tens or hundreds of data points, and they make the world's best robots as a result of that. But it's not automated. So it depends where you want to be here. But there's another axis here which is important, which is how likely are different things to generalize. And it's important to realize that generalization is really about priors. It's about, prior structure that you put in. It's not about the data. And so I think having models that are inspired by physics and reflect our prior knowledge is a good thing. And then we want to learn, of course, but we don't want to throw away Newton's work, along the way. So how is this approach in general works? Design a physics model using your knowledge. You fit parameters to data. So this is a form of learning. It's called system identification. If engineers want you to be fancy and get VC funding, they would call it learning, but they don't. You need a Bayesian estimator, which approximates Bayesian inference somehow, Kalman filters and such, particle filters. Feedback control, this is what the reinforcement learning and optimal control do. You want to test things in simulation, deliver perturbations like what Vincent was showing to make sure before you deploy it in a real system that the thing, at least in simulation, is not too sensitive. Of course, you want to collect the real data, then find ways to improve all of the above. Now, a few comments here. If you look at the reinforcement learning and deep neural network methods that are attracting a lot of attention, they require very large amounts of data for now, which is being collected on simulation. So effectively, they are model-based in the sense that there is a model there. They're just shy about it, and they don't want to admit it too much. Of course, one could promise to improve data efficiency, but similarly, one could promise to improve the accuracy of the models. Now, there are many examples where we already have physics models that allow us to do dynamic tasks that are accurate enough to be deployed. And this is mostly all the work. I just want to remind you, just to make the point. So this is work that made Peter Bill famous at the time. So he basically modeled the physics of a helicopter and made it do incredible things that, it's still amazing that all this could happen. No, shut up. Sorry. This is work that we did in my lab where we set up a model of a robot bouncing a ping pong ball, and then you can go and perturb it, and you can give it various heights, and it's very reactive. You can give it another ball, and it kind of happily bounces it. So are these models perfect? No, but they're good enough to make, so this is using trajectory optimization in real time, known as model predictive control. We have shown a little bit of that. This is pretty amazing. This is my former postdoc, Emo Todorov, who's now at Georgia Tech. So they have a model of a car that's running on a GPU, and they're doing model predictive control in real time on the car through optimizing through the physics about maybe a second ahead. And it's doing sliding and crazy things that probably the model is not very accurate, but it's happily driving. In the latest incarnation of that, they actually collected enough data on this specific track to fit a neural network model of the physics, and then they're still planning through the model, and that's working slightly better, actually. But still model-based, just the source of the model is different. This is something we did in collaboration with Sergey, actually. So here the model, it's still a model, but it's a simple model. It's a time-varying linear model that's collected from data on the real system, and then we do trajectory optimization through that model with a modified form of accuracy that Sergey came up with. And after surprisingly small number of iterations, it learns the task is to make the object spin, like do whatever you want, just make it turn by some 90 degrees. So this is like 15 trials on the real system, and it makes the movement. Of course, it's highly overfitted to that motion. We'll see a bit of generalization later. And finally, this is an example where we are doing robust control. Instead of doing the adversarial thing, which actually is a good idea, what we're doing is something simpler and much more efficient to do. So we just take 10 different models that are different in their masses or some joint parameters, and we ask a single controller to work for all of them in simulation. And the idea is that if it can do that, it can probably work for everything in between, including hopefully the robot. And so these are movements that are fully optimized in simulation. Then you play it on the robot, and they work with about 90% success rate on average. Just a little Darwin getting up from the floor. And of course, if you look at the real world, most machines deployed in the real world are operated in some such way, which is cars, airplanes, drones, chemical plants, NPC, sort of the standard for controlling chemical plants, power grids, industrial robots. Part of it is because this is classically how things have been done, but there is another important component to it, which is whenever you do something with real machinery, you have to guarantee safety. So you can do all the learning and NIPS papers you want, but if you try to convince the control engineer to deploy that, the first thing they're going to ask you, well, is this safe? And if they notice that you haven't even thought about it, that conversation tends to end right there. And how do you guarantee safety? Well, you kind of have to understand things before you guarantee it. And if you don't understand what a deep network does, how can you guarantee anything, really? So that is a bit of a philosophical issue that we have to work on and hopefully develop techniques. Maybe some of these adversarial techniques are actually getting there, because if you can show that you tried to break it really hard and you couldn't, then that's probably a good sign that it may actually be safe. How good are existing function approximators? This is a bit of an aside. So this is kind of interesting. This is a very rare, sort of honest view of what actually is going on. I wish more people in deep learning did that, but our friends at DeepMind decided to see. So they have the Q learning, and they're asking how well does it match the empirical returns. And on simple tasks like pendulums and car balls, it's actually pretty good. So this is the true empirical return. This is what Q network does. Once you go to something more complicated, it's a nightmare. And this is not even that complicated. So now you can say, well, performance is still good, so who cares? Well, but you have to ask yourself, why is that? Why is performance still good? Could it be that, how can you do something sloppy and get good things out of it? Could it be that the task itself is somehow easy? And so that's something we ended up asking sort of by accident. My colleague Sham Kakaded, who is now at UDAP, has an algorithm for telling easy versus hard. And it's a brilliant algorithm. It says, try the dumbest thing that's not entirely stupid and see if it works. If it does, then the problem maybe is. He's also the person who came up with the natural policy gradient, by the way. Then another good algorithm. So we did that. We took linear feedback controllers, simple mapping from positions and joint velocities to actions, and try to train them in the same task that people are training humongous deep networks. See what does it do. The other thing we did is something called RBF. So Sham is a big fan of kernels. So the RBF kernel needs an infinite feature map, but actually Ben Recht here and colleagues show that with a small number of sine functions applied to random linear projections, you can approximate it very well. So that's our RBF policies. and we trade them on the RL gym tasks. And we found that they're actually very competitive with the state of the art. So what you're seeing in these plots is these are different tasks. The green thing here is the best performance with the TRPO. That's on RL gym task as of February. And yeah, we're basically doing what people are doing. In this case, we're even exceeding it. The red thing is the linear policy. So in most cases, linear policy actually gets pretty good to the base neural network, and the RBF almost always gets there. So let's look at that. Okay, so this is a linear policy making a hopper hop. This has a total of 33 numbers in it that have been learned. This is an RBF policy. So there's 11 states and whatever 3 controls, so that's 33 numbers total. Here's a linear policy making a walker walk. You can ask, how on earth is that possible? I mean, I've been doing control for 20-some years. I didn't know a linear policy could do that. In retrospect, it's not that hard to imagine because we have these things called passive dynamic walkers. You know, these toys that you put them on an incline, they actually walk just because of the physics and no control at all. So given that we have those things, it's not too surprising that you can find a simple way to excite a system such that the physics does the rest and produces some very interesting looking motion. Not because you did something hard, but because you just picked a very well-designed system. And indeed, in locomotion, the hardest thing is stability. If you can ensure stability, and you don't have to worry about it, and 2D basically ensures stability because you can't fall sideways, then any excitement to the system is probably going to produce some progress in some direction, which you can then call locomotion if you want to. And then Carl Sims demonstrated that in the 90s. Like he basically used evolutionary computing to actually evolve both bodies and locomotion controls, and he was very successful. Now, one thing I want to illustrate here is something that also Vincent talked about. So these things are badly overfitted to a few initial conditions. So here is some kind of walker that just falls and doesn't walk. Here we that. So I think a lot of the people who publish papers in this literature, if they were to deliver perturbations to their systems, they're going to realize that they do just that. Turned out there is a very simple way to actually overcome it, which is to basically train from a diverse number of initial conditions. And not too many, just like 10 basically. And so once you do that, now we're going to perturb the thing. It heroically does something and keeps, so these are policies that know how to both to get up and do a task. And you can also get a linear controller. I'm trying to find it here. So here's a linear feedback controller that can both get up and start hopping. And again, a total of 33 parameters, I would learn the dumbest possible thing. So that's some food for thought there. Now, there are other interesting architectures that are not deep networks that are very promising and worth looking into. Something that came from graphics that I always like, this is a thing called Symbicon. It's 10 years old now. So what they do here is they build a little state machine that corresponds to different phases of walking. And then in each state, they have some, so these are little state machines. And each state, they have like a really simple controller. So usually linear and a couple of hand-picked features. And these things are very easy to design by hand. So I've had undergraduates who know nothing about control build these things in a few days in undergraduate classes. And then they can put this thing together and make things walk in fairly robust ways and get these perturbations and do stability and do a bunch of styles, etc. So of course, these are graphics people. They are really good at making things look good. But so you have to apply a certain discount factor to that. Actually, Sergey used to be one of those, so he's laughing because he knows what I'm talking about. More recently, they did that instead of having these little modules designed by hand, they actually used modular architecture of Actocritics, and that was in SIGGRAPH last year. The first author of that, Jason Peng, is coming here because Peter managed to recruit him to our great disappointment. We tried to, but it didn't work out. So another thing along these lines, which is another, not a neural network, but something else actually works really well, is actually what Boston Dynamics does. And again, if you've probably seen the videos, and these guys make the rest of us look like a bunch of useless academics writing papers, basically, which is exactly why Boston Dynamics was set up. Mark Rabot was an extremely successful academic, but he decided academia is not good enough, and that's not the way to solve big problems, and created Boston Dynamics. Sadly, they don't really publish what they do, but last time we asked Ritzi, what do you do? He said, well, I can't tell you, but basically it's the same thing we did 20 years ago, only slightly better. So what did they do 20 years ago? There's this theoretical idea which is really nice. So there are these funnels. The idea is that you have these regions in state space where you create a controller that within some region it knows what to do, and it's going to kind of bring the system in some controlled way to some other place. And now you have another controller that can take over from there, and then if all these controllers cover the whole space, then you're done. And so the overall approach there is you're trying to get some complicated thing to work. You get some basic control and see how it fails. And then say, okay, for that failure mode, I need to think of a different control that's also simple, but it's adapted to that mode. And then I need to think of some rule for switching between them. And then you run it, and then if it's another failure mode, you add that. And how many of those modes are there? Well, they're not that many. They're probably on the order of 10 or 20, or on that order. They're not like thousands. So this kind of architecture, I think, is actually very promising. It should be explored more, and this work is actually one of the first to kind of try it. We actually did something very similar, kind of, again, mostly by accident. So it's a continuation of this hand project. We decided to look for generalization that was done by Vikash Kumar, who apparently made it to Berkeley today. So the goal was to get, sorry, this is the learning on the previous thing. So here we actually have an expert demonstrating a bunch of movements, picking up the object from initial conditions. This is done with VR in a simulation. And then what we did is we did our old work where we train a local controller for a single object orientation. And then when I give you a new object, what happens is that we look in our database of controllers, find the nearest neighbor based on the initial object orientation, and just run that and see what happens. And of course, you can compare it to a neural network, which Sergey and Abhishek here did while we're collaborating. And it also does something, and you can also run it on the real robot. It's a scary robot that's in my lab at UW. And so to my surprise, actually, the nearest neighbor here ended up doing better than the neural network. So this is the performance of the nearest neighbor. This is a number of different ways to train the neural networks with different things being in and out. And again, this is one of those, dumbest things that are not entirely stupid. In fact, I kind of suggested to Vikash to do it for 3 days before the conference deadline, and it ended up working quite well. So I'm seeing a lot of cases where, yes, you could have used a deep network, but if you use something else, it might work just as well, and it's simpler to understand and simpler to build. And I'm not saying don't use deep networks, but I'm saying don't take it from vision and just assume that it's going to work in some domain that actually has very different properties. Think about it first. Now, I want to switch gears and talk about, so if you're going to do model-based optimization and you won't do it aggressively, you want to have a physics simulator that can support that. And you have to understand, whenever you do that, we're doing some form of adversarial training, as actually Carl Sims discovered in the 90s. So whenever you have an optimizer sitting on top of a simulator, you think the optimizer is trying to solve your problem, but no, it's trying to cheat. It's looking for loopholes in the physics simulation that can be made to do the system crazy things so that the task is magically satisfied. That might involve like extracting energy from the floor, even though that's not supposed to be possible, or just somehow breaking the robot apart so the pieces just fly there, whatever. It's trying its hard. It's best. So you really need simulators that are not only fast, but also very robust and cannot be cheated. And so the reason I ended up developing MuJoCo is because I realized that the lack of adequate simulators is blocking my research agenda, and I don't like that, so I decided to unblock it. Just going to tell you very briefly about the mathematical framework, and then we're going to see how we can exploit some of these properties, not only to do simulation, but also to do control. Some notation: Q is a configuration, V is velocity, tau are applied forces. Internal forces are things like nonlinear interaction force, like Coriolis centripetal forces that you get in a multi-joint mechanism. M is an inertia matrix, very important. There are fast algorithms to compute it. J is a Jacobian that maps from joint velocities to the velocities of contacts. You get that from collision detection. And constraint forces are things that are hard to compute. So everything up to here, this is basically a done deal. There is a book by Rory Featherstone, which is the Bible in that field. You just read it, it tells you exactly how to do it. Computing these constraint forces, there is no closed form solution. You actually have to solve an optimization problem and solve it at each time step, formulate an optimization problem and solve it at each time step of your simulator. Traditionally, the classic thing is the approach developed by Trinkel and Stewart and also Anitescu, which is formulates this as a linear complementarity problem. Unfortunately, that's NP-hard. So you don't want to solve that in real time. The various physics simulators, including Bullet and OD and NVIDIA and such, approximate that in fairly aggressive ways. There are actually not guaranteed to do anything sensible because they had no choice but to really approximate it. What MuJoCo does is takes a different approach to that. Instead of trying to start with an NP-hard problem and approximate it, it actually tries to formulate physics as a convex problem, which we can then solve. And the formulation that comes out, which I'll tell you in a moment how it's derived, is this. So you define the acceleration of the system as the solution to an optimization problem. And the optimization problem is the following. You have this term here that basically has F equal ma. So this is Newtonian physics. So you're saying, basically you're saying you deviate from the unconstrained physics of the system as little as possible, while at the same time minimizing some penalty for constraint violations. This R is a reference acceleration that you compute, saying that if you penetrate, you want to go up. So this magic function S is where that's what the secret sauce is based, which is not at all secret because the math is on the website, and well, it's effectively secret because people won't read it, but apart from that, it isn't. It's a convex C1 penalty function. So when you use cones to approximate, when you use pyramids to approximate friction cones, this becomes a quadratic spline. The nice thing about this formulation, apart from the fact that you can solve it quickly, is that you can actually get an analytical inverse dynamics. So even though in general contact dynamics are not invertible, meaning that if I'm pushing against this podium, looking at the kinematics of my motion, you cannot recover the contact force because the podium is eating away the force without any motion. But when you have a soft constraint model, the more I push, it's going to penetrate a little bit. And that penetration is enough to recover it. And of course, the harder the parameters of the model are, the less penetration there is. Since the forward dynamics is a solution to an unconstrained optimization problem, there's a unique global minimum which sets the gradient of this thing to 0. And the gradient is that. Okay, so this is the applied force, and this is the acceleration we're looking for. If we're given the applied force, solving for acceleration requires some numerical procedure because acceleration appears as an argument in this quadratic spline. But if we're given acceleration as in inverse dynamics, then this is just an explicit formula we evaluate, and we get the applied torque essentially for free with almost zero computation. You can also differentiate this thing one more time, and we get the derivative of the applied forces with respect to the acceleration, so as the derivative of the inverse dynamics. And if you want the derivative of the forward dynamics, you just take the inverse of that matrix. And what it is the inertia matrix, as you would expect, like you have F equals ma. If you differentiate with respect to A, you're going to get M, as you expected. And then you're adding something to it. And what this is, it shows you that the constraints are acting as added inertia in the space of the constraint. So basically, they're stopping the system from moving. But it's not like a spring damper that needs to stretch before it notices something bad happen. This is actual inertia there, so it stops you from accelerating in the first place. How is this thing derived? I'm very quickly going to go over it because it's probably not the field that you care about, but I do. So there's something called the Gauss principle of least constraint, invented by Gauss clearly, which is equivalent to Lagrange-D'Alembert equations, and you can get constraint physics out of it. So it says minimize the discrepancy from the unconstrained dynamics subject to whatever constraint you have, in this case, acceleration cones. You can take the dual of that, and you have a optimization problem over constrained forces F, and this is the inverse inertia in constraint space. And you have to solve it in a constrained way. And so both of these correspond to hard constraints, and actually, even though they're convex, they don't give you very nice physics. So what I did is I augmented the dynamics with the constraint deformations. Sorry, I'm glossing over this because it's actually not that interesting now I think about it. And you can do convex duality to get a constraint problem, or you can come up with a primal unconstrained problem, which I showed on the other side, on the other slide. So all of this is implemented in a version of MuJoCo that just came out last week. So there actually, for those of you who are using it, there's actually a pretty big change in the constraint solvers. They're now a lot better. You can have a sparse or dense Jacobian for your constraints, or auto, which is going to switch automatically. You can have pyramidal elliptic friction cones. There are 3 algorithms. Projected Gauss ideal, which is pretty much what every simulator uses, and MuJoCo used to use it, relied on it pretty much exclusively until a week ago, but now it doesn't. And then there are Newton and conjugate gradient methods to solve this unconstrained convex optimization problem over accelerations. The way you specify these things is there are some new options you can find in the documentation. So the Newton method uses an exact Hessian. It uses a direct Cholesky factorization, then being incrementally changed with one rank 1 update, so it's very efficient. CG is the PRP formula, the Pollock-Ribieri plus. Does essentially exact line search shared with Newton. PGS does something clever when you have elliptical cones, basically does ray search followed by QC, QP over the contact surface, because regular PGS does bad things. So let me just illustrate something. So this was inspired by a conversation I had with Wojciech at OpenAI a few months ago. I asked him, well, what do you want MuJoCo to do? He said, well, I want a robot with 100 objects I can simulate efficiently. And at the time you couldn't, you could, but it wouldn't be efficient. So since, they're valued customers, I decided to do that. So here's a robot with 100 objects. This thing now has a built-in profiler. So this thing on the side is the conversion. So this is the norm of the gradient of the cost functions being optimized of Newton method. And you can see that it basically hits, so on the y-axis is the log 10. So basically it goes to 10 to the minus 13. So essentially, for the first time, we're actually solving these contact force problems exactly. And you can do things like you can sort of disable warm start. So now you can see how it's going to do it. You can see that these balls over here are actually stacking. So it does not break symmetry until some rolling cylinder hits the thing. The CPU time is about a millisecond for this kind of simulation. You can do other things like here's Jenga, for example. You can kind of select it and pull things. Here the CPU time goes down to like half a millisecond per time step. And you can do other things like here's a hand with a bunch of boxes, and you can, sorry. How's that thing work? You didn't bring your glove? I totally need my glove, yeah, tell me about it. God, this is annoying. Sorry. Why is this? There is a way to make this thing turn, but I'm not very successful with a Mac running Windows that doesn't have a right button, sorry about that. So anyway, so you can play with the new version of MuJoCo. Is qualitatively better than the previous version in terms of the solvers. Now, we're going to use this. How much time do I have? Okay. When do you want me to end? 12:35. Okay. So now what I'm going to do is I'm going to exploit the unique properties of this contact model to do control faster and more efficiently. And I'll arrive at something that, even though I'm doing it from my more traditional perspective, it's also very useful for you if you're doing reinforcement learning. You'll see why. So here's the idea. It's a very high-level idea. Suppose you have a robot, and you may send control voltages and such to it, but those are hard to compute. What if you had an optimizer that was built into the robot, which allowed you to control the robot with instantaneous cost functions rather than controls? And then what it did is within, let's say, a millisecond or less, it optimized those cost functions and computed the controls as the minima of these cost functions, then control the robot for you. So in that way, you can try to control the robot on a high level. The examples of that, so for example, operational space control pioneered by Osama Khatib here at Stanford is an example of that. You take the robot dynamics and you project them into an n-effector space and express all kinds of quantities there, and then you map through Jacobians. Another thing which is actually very popular in robotics these days, especially in sort of humanoid robotics, is reduce the model somehow, let's say inverted pendulum or something, then formulate an instantaneous control as a quadratic program, solve it, and then map on the degrees of freedom. And that the quadcopters also use that, like Vijay Kumar and such have used that to fly them very successfully. Problem with this approach is that it ends up treating the joint torques and the contact forces as being independent variables that you dump into the QP. But in the real world, they're not, because if I choose some joint torques, that's going to elicit specific contact force and not just anything within the friction cone. So you can think of this as generalization to what's going on in robotics right now. The idea is the following. So we're going to, as I said, we're going to control the robot with instantaneous cost functions, and we're going to let the robot come up with its own controls in real time. Okay. So some notation. So tau, we're going to partition the control force into things that we can control, sorry, the applied force, into our joint space, which you control, and then Z is a null space. For example, if I'm a humanoid, the position orientation of my torso is null space. I cannot control it. F is going to be forward dynamics, G is going to be inverse dynamics. Okay? So the forward definition of this goal-directed dynamics is the following. The acceleration of the system is given by my forward dynamics, given my position and velocity, so that's the state. And then the control, the user doesn't have to give me the control. Instead, I'm going to compute the control for the user. And how I'm going to do that is I'm going to optimize some energy cost, which is just the norm of this control signal, plus a cost function that the user gave me, which is evaluated at the next state resulting from the control that my optimizer is currently considering. Okay? So you can probably recognize that as the inner loop of the Bellman equation. I'll make that more explicit later. For now, this L is just given. Normally, it will be a value function approximation. Alternatively, you can talk about inverse dynamics and say, instead of optimizing over controls, I'm going to optimize over accelerations. And now, in order to compute this, I need the inverse dynamics to give me the torques, and then I penalize them. And then this is just a function of accelerations instead of pushing the forward dynamics. So this is a lot easier to optimize, and conveniently we have inverse dynamics, so we can do that. So just to summarize how these things relate to each other. So in forward dynamics, you're given applied force, and you want your model to compute both the acceleration and the constraint force, like contacts, joint limits, etc. In inverse dynamics, you're given the acceleration, and your solver computes both the applied force and the constraint force. In goal-directed dynamics, you're not given any of those. You're given some kind of cost, and it computes all of the above such that they're consistent with both the forward and the inverse. So this is a generalization of both forward and inverse. It kind of does both at the same time. Now, why is this hard? Because contacts make the relation between applied forces and accelerations piecewise linear at best, and somehow piecewise conic if you have elliptic cones. And if you have n active contacts, you have 3 to the n such pieces. So just to be clear, what I'm talking about is instantaneously switch. So the dynamics is basically hybrid. So if you're in contact, instantaneously you can decide to push that way, in which case the contacts will break. Or you can push that way, in which case it will block you. Or you can push that way, in which case you're going to slip, but after you overcome friction. Right? So this is not about, over time things penetrate. This is like at each point in time, your controller has the freedom to choose from 3 to the n pieces, and then in each piece there's some kind of dynamics. And so how do you know which piece to pick? If you look at things like IOQG, it picks one of the pieces and keeps its fingers crossed, basically, which is a big problem with these algorithms, and given that, they can now be upgraded. So what goal-directed dynamics does, it tries to optimize over all these pieces, but instead of doing combinatorial optimization, it's relaxing it into a real valued problem. And the way it does that, again, this is the formulation. You compute gradient. You can compute a Hessian explicitly, and now the Hessian is piecewise constant, and the gradient is not smooth. So this is a non-convex, non-smooth optimization problem. You might think it's nasty, and it is. The good news is that the primal dual methods are exceptionally good. And so if you tune them carefully, you get the following. So here I'm going to show you a simulation where I'm using the mouse to specify a cost function in real time. And the way I specify a cost function is I select a body, and I put the mouse cursor somewhere. And the software is saying, OK, I want this body to accelerate towards that cursor position. So I'm going to define an instantaneous cost over accelerations, which basically says, dear selected body, please accelerate that way. Okay? So it's a very high-level way to control the system. And then it's going to look at the dynamics, look at all the contacts that happen to be active, and ask itself, what joint torques do I apply right now, such that after I take into account all the complexity of contact dynamics, the selected body will happen to accelerate that way. Okay. So let's watch. So here is the thing. Okay. So now this is what I talked about goal-directed dynamics. I'm basically controlling this robot with a goal. The robot knows what to do with its body such that to make the selected body part move towards the thing I'm moving. It is completely greedy, so there's absolutely no planning here. The planning is all happening in my mind. The optimizer is instantaneously at each time step is saying, OK, how do I make progress towards this thing right now? But it's not assuming anything like the contacts or equality constraints. So basically, it can make them sleep or break or roll or whatever is necessary. Here's a situation where some kind of gate emerges out of this. No planning whatsoever. It's just that basically the contacts happen to make and break in a sequence that it can leverage them. So it's almost like a little baby that's lying on the floor and trying to reach a toy, but doesn't have much of a intent or planning yet. This is the Adams family hand. We can tell it to move its palm up, and it uses occasional sort of contacts between the fingers and the table to do that. And it's going to flip at some point. It's very difficult to control Adams family hand, it turns out. If you have a fixed base system, this is trivial. This is just, you basically can do like end effector control. You tell it where to go, and it goes there nicely. You can tell it to achieve poses. You can tell it to move the thing while grasping. So like kind of quasi-static things, this actually essentially solves them for you. But these are not the interesting ones, of course. The interesting ones are the dynamic ones. How quickly does that work? So I was really surprised with this. I thought that if this works 10 times slower than forward dynamics, I'm still happy because it solves an incredibly interesting problem. It turns out it only works 2 times slower than forward dynamics. So here's some timings. This is the humanoid, this is the hand. These are microseconds, not milliseconds, microseconds. Forward dynamics on the humanoid takes about 50 microseconds to execute with about 10 contacts. With the new MuJoCo, it takes 35 microseconds. When you do this goal-directed computation and then run the forward dynamics with the controller, the lower level compute it for you, it takes 100. So it's basically 2 times slower. These are various statistics showing that the primal duo method really solved the thing and satisfied the constraints and found at least the local minimum. Cannot guarantee a global minimum. Of course, nobody can in a horrendous problem like that, but the local minima seem to be good enough. Now, as I alluded earlier, this relates to dynamic programming in an obvious way. So here's how we do it. Just write down discrete time integration. This is position, this is velocity, this is acceleration. Assume some running cost for an optimal control problem where, again, this is the inverse dynamics. So this is the control forces. You penalize them. It's the energy cost. And then P is some kind of position-dependent cost that says, make the world reach some state. Okay? So the Bellman equation for the optimal value function is this immediate cost plus the minimum of your energy cost plus the value at the next state. Okay? So this is standard. This is all the dynamic programming and reinforcement learning and such are basically derived from these things. Now, notice that this minimization here is exactly the minimization that goal-directed dynamics solves. If I pick this magic cost that I was setting with the cursor to be the value evaluated at the next state, this is a function of acceleration because the next state depends on acceleration through my Euler integrator. Okay? If you set your Q function to be in that form, the immediate cost plus the value function, then you can use GDD to solve the action maximization step in Q learning in 100 microseconds for rather interesting systems. And this has quite a few applications. Let me, so you can use for teleoperation like I showed you. You can generalize the QP-based approach to control what robotics are doing. There's a new trajectory optimization coming based on this. Is going to be called AI LQR. It starts for acceleration-based iterative LQR, but AI is popular these days, so I thought I have to have an acronym. Q-learning, where the optimization of actions is taken care of by the simulator, so you don't have to worry about it. You can also train neural networks controllers in policy gradients that output accelerations rather than controls. And actually now I worked with Igor Mordak a couple of years ago. We did exactly that, and that turned out to be easier than computing controls. And at the time, Igor cooked up some kind of inverse dynamics on short notice to map from accelerations to controls, and we now have a better way of doing it. So I want to end with a bit of philosophy. There are 2 philosophical slides. I can only have time for one of them. Let's talk about this one. Okay, so there's this picture, right? There's agent, environment, action, and then the environment sends observation and reward. And I'll argue that this is not a fair assumption. So in the effort to be model-free, RL treats the reward as being externally generated. But in that case, this assumes more, not less. It basically assumes that you have an oracle out there that can give you reward. And that's just not true in biology, and it's not true in robotics. And so let me actually go through the argument. So if you look at how brains work, we now know that the brain has very elaborate neural mechanisms to compute the reward internally. So in other words, you don't work for food. You work for dopamine or serotonin or some other neurotransmitter. And indeed, if you're a drug addict, you stop working for food because you're getting the reward directly. And there's some psychiatric disorders that also do that. Why is that? It's probably because the objective rewards are too sparse in time to be useful. So for example, consider a predator chasing prey. If it only gets reward when it eats the prey, well, how many prey does the predator chase in its lifetime? Thousands, maybe? You can't learn a complex sequence, hiding in the bushes, stalking the thing, chasing it, adapting to it, eating it, peeling off its skin, whatever, with 1,000 bits of reinforcement that you collected. You'll die long before that. So, and indeed the brain has discovered that. It says, well, we're not going to get the reward only when we catch the prey. We have our basal ganglia that's going to figure out, oh, we're getting closer to the prey, therefore, dear brain, great, good job, do more of that. That means that this reward thing is actually built into the head of the agent for any biological system that basically has a brain. And the others don't learn. The others just adapt. Now, what about robotics? So I think eventually we want robots to be able to compute rewards for themselves. Can't expect a human to do there and say yes, no, yes, no, yes, no. Then there are a number of demos now where the world is instrumented with a clever little sensor that just happens to give you a notion of task completion. But I think that's a cheat. And the reason it's a cheat is because the places you can put those sensors are also the places where you can put a simple actuator that just does the job for you and you don't need a robot. So a lot of these places press a button. Why on earth do you want to press a button? The button has a circuitry inside it, just send an electronic signal and be done with it. Or adjust my thermostat. Well, the computer can do that for you. And so I think in general, we have to assume that robots will have to operate in environments where the robot is the only thing that can tell is it doing well or not. And that basically means a general purpose perception system. It's also good to have that because if a human wants to explain to the robot what to do, you can do some of it. So there's interesting progress in imitation learning, like trying to infer goals from what the human is doing. But I think there's plenty of overfitting there for now, and we'll have to see how far it can go. But certainly, if you want to, let's say, put an object on a table, a human can say, what that means is that the XY coordinates of the object are over the table. That will not overfit, it will generalize properly, etc. But for that, the robot needs to understand what's a table, what's XY coordinates. It can't just be looking at pixels. So basically, if you want to communicate with the robot, communication implies a shared representation. And humans happen to have a certain representation of the world, which is actually very similar to what physics simulators do. In fact, that's why they do that, because they were designed by humans. You could still do, of course, things like end-to-end training, but they're not instead of such a perception system. They're in addition to it, I think. And so then you have to ask yourself, well, is it really worth it, or do you just want to use your system as a preprocessor? So OK, let me end on this bit of philosophy. Thank you.
Say that presentation was quite amazing, and I would like to thank you for MuJoCo 1.5. Actually, I think it's very different than previous versions of MuJoCo. It's actually extremely accurate and extremely fast, so I recommend it to everybody.
Unlike what it did before.
There is no question.
So are you guys going to switch to it? It's actually, so the people at OpenAI have done more to make MuJoCo popular than I have, which is, shame on me. But as a result, most people using MuJoCo through OpenAI. So unless they upgrade, nobody else is going to upgrade. So I hope they do.
Yeah. Thank you.
Hi, thank you for a great talk. So you mentioned moving away from end-to-end. You also mentioned state-dependent mixtures of models. And I was wondering, this is sort of like a shallow hierarchy. So do you think about moving to deeper hierarchies? Is that the direction?
So shallow, I think the mixture model, the shallow mixture model should be, again, do the dumbest thing first. If that runs out of steam, sure, let's do deep hierarchies. But has it run out of steam? No. I mean, most of the work has been done with manual tweaking, and we know it works, right? I mean, look, if the engineers at Boston Dynamics can optimize a controller with like a couple hundred parameters by hand and get Atlas to roam through the woods, why are we not learning in that representation? I mean, why on earth would you learn 1,000,000 parameters when you can learn 100 and there's an existence proof that the thing actually works? So yeah, deep hierarchies could be good, but let's do simple ones first and see where they run out of steam and then go to the deep ones.
You mentioned, oh, sorry, it's Ken. I'm right here.
Oh, okay.
Thank you. I want to say a little more about this this slide here behind you, because so your conclusion is that there has to be an internally generated reward function, and then you said as a result you must have a general purpose perception. Can you elaborate on that?
Well, so the reason I say general purpose perception, because you cannot define success in image space. I mean, okay, say I want this bottle to be here, fine, but you can turn off the lights, I can occlude it. All the invariants that come into perception, they come in here as well, right? I want that to be the case, not something about the images to be the case, or something about the configuration of my robot. So that's what I meant by general purpose perception system. Usually, when we talk about a state of the world, we really mean the true state of the world, not some kind of sensory description of it. And by general purpose perception, I mean the thing that takes sensory data and infers the states. That may be a bit of semantics, so I'm willing to be somewhat flexible on like what exactly does that general purpose system do, but sensory invariants are something that it has to do, I think.
Okay, so that's one part of it, but there's another thing you were getting at, I thought, which when talking about the prey example, right, that you need to get this feedback before you actually catch the prey, right? So in some way there's a sense of progress.
Exactly. So your internal reward mechanism is essentially figuring out, are you going to get the prey or not, and spreading out the reward through time. And so effectively, the learner is actually getting a time, a reward signal that has a lot of information over time. It's not just waiting you to get the prey. Now, it's interesting, like, where did you come up with that reward function? Part of it is probably hardwired, because organisms would really be dying in large numbers if they were not born with something along these lines. Part of it is probably learned. It is not learned through reinforcement learning. Actually, that's kind of interesting. That system is very carefully protected from reinforcement learning, because if it wasn't, what's the optimal thing to do? Max out the dopamine in your brain at all times and be happy, right? You can't do that, right? So the system in your brain that learns whether the situation is good for you, it cannot use its own reward to reinforce itself, or else bad things happen. What kind of learning is that? Well, it's some other form of learning that actually would be nice if we were to study it more. I mean, people like Peter Dayan and Schutz and company have connected that to reinforcement learning. So the idea of temporal difference learning and reward prediction, like a lot of the little terms that show up in reinforcement learning actually have correlates to the neurostructures that signal reward. But the point is that that mechanism is inside your head. And if it's there, you might as well assume that you have a model of reward and take advantage of it.
It's always like you answer a question and it's like there's like 10 more hours of questions that have come up there. But just to follow up on that last point, just the measure of progress idea, right? That how do you relate this to general purpose perception? Is it a matter of not just coordinate invariant, but something more that's going on?
Yeah, I think there are two things. So what I have in mind is that design a function that measures progress given access to the state of the world, and then you design a perception system that maps sensory data to some abstract notion of state, which is suitable for measuring progress. That's what I'm talking about. Because you're my student, you could have asked the question 5 years ago. I'll take that question.
Thanks, very interesting. So in the well-directed dynamics, how sensitive is that to errors in the model?
It will give you, I mean, the short answer is I should try it. It's trivial to try. It's going to give you some contact forces that are specific to the model and to the state estimate that you have right now. What are these contact forces going to do? I mean, if you're lying on the ground and you're trying to lift your arm up, it's probably not sensitive. If you're trying to hold something by the edge, it's a precarious situation where it's probably much more sensitive. But yeah, it's worth looking into that. But if you fold that into a learning framework where you use goal-directed dynamics to optimize this, but then you have a learner that learns that. This learner could, for example, be an ensemble learner where it fits a value function to an ensemble of 10 different models. Or with a model where you intentionally inject noise in the state estimate to force it to be robust. All right, thank you.
Excellent.